Okay, so first, thanks to the organisers for this chance to tell you about AMPLE. AMPLE is our molecular replacement pipeline. We call it unconventional molecular replacement. And what it's about really is exploiting bioinformatics methods, particularly structural bioinformatics methods, to really extend the reach of molecular replacement to ever harder cases. So cases where there's a homologue but it's very divergent to yours, or even completely novel folds. So in the time available, I'm going to keep the introduction to an absolute minimum. It's going to be 2 slides explaining why we call AMPLE unconventional, and one a kind of overview. Then I'm just going to go through quite quickly a series of scenarios in which you might think of using AMPLE, because AMPLE might solve your structure for you. I don't know if that's going to stay there. So, conventional molecular replacement usually employs known structures from the PDB, either as the crystal structure, occasionally as homology models. One of the things we do with AMPLE for unconventional molecular replacement is ab initio modelling, which is a way of predicting a protein structure without the benefit of any known homologue in the PDB. It works by taking the sequence and essentially stringing together little fragments of protein structure which may not be related at all, to produce a structure prediction. There's been also talk about ensembles, but I think probably conventionally people would lean towards mainly using single structures, whereas AMPLE, as you'll see, is almost exclusively about ensembles. You might try a few, or a medium number in an automated fashion by conventional MR, I should say. AMPLE produces tens or even hundreds of different search models and trials them automatically for you. As Ronan was mentioning, it's not unusual, the idea of editing a crystal structure before you try and solve your target with it. But generally you would restrict yourself to trimming a few loops here and there, losing a few side chains. What we do with AMPLE is much more dramatic editing, sometimes even down to 10% of your starting structure. And what we find quite regularly is that kind of dramatic editing is really required for success. So we go beyond the kind of manual, gentle editing that's conventional. These are excellent pipelines for conventional molecular replacement. We put ourselves here with Archimboldo and Fragon as unconventional molecular replacement. So what does AMPLE look like? It's a pipeline. If I start on the right, AMPLE serves to generate search models, which it feeds to Mr. Bump. You've just heard about that. It places them with phaser and molrep, and then optionally you can connect those results to this excellent software from other groups which will trace those results, possibly rebuild it for you. So when AMPLE works well, you may well end up with a relatively complete, automatically rebuilt structure. And like Ronan mentioned, we particularly appreciate ShellXC for the statistics that give you a pretty definitive answer as to yes, no, I have solved my structure or not. So the clever bit about AMPLE is really over the left here, where we're using bioinformatics to do unusual model building or to treat experimental structures in unusual fashion. We started off with ab initio models, like I say, globular proteins initially, then other classes, and I'll talk about these. These all generate ensembles. We looked also at NMR ensembles, treating them in the same way. And more recently, we've been working with superpositions of several distant homologues and more experimentally ways of working with single distant homologues to get maximum value out of them in difficult cases. And this involves a program called Concord. So to start with, historically, what we looked at first was ab initio modelings. And like I say, the idea here is to enable molecular replacement with new folds or really very divergent folds. And I won't go through any of the details here, but the ab initio modelling is done by programs like Rosetta and Quark. This is a little bit of ab initio modelling in action. Done to its maximum potential, ab initio modelling is very slow, but we do a kind of quick, crude version, which turns out to be good enough for our purposes. So we would make about 1,000 models here, and we would look at them and try and cluster them to find groups of structurally similar models. And if you can find a large number of similar models in your set, that's a sign that the modelling has probably worked quite well. You take those clusters and you do a truncation. This is a very important part of the way AMPLE works. AMPL truncates progressively a set of structures like a cluster here, eliminating first 5%, then 10%, and so on, right down to 95%. And that's a rational truncation because within this cluster we can actually predict which parts of the modelling are good and where the modelling is bad. And the way we do that is by scanning along the sequence and looking at the structural variability of each region. And where the models vary a lot, that's a sign they're less likely to be reliable. Where they've all reached the same conclusion, they're a bit more confident. And so obviously we start off the truncation by eliminating the very variable bits and progressively work our way down. So we produce sets of search model ensembles, and they're ensembles because we've done a superposition of multiple structures at this point. Search model ensembles over a range of sizes here. Then we sample among those truncated clusters at different thresholds of structural divergence, try different ways of treating side chains, up to 180 search models per cluster that we look at, and then it's fed through this software here. So the first results we got with this approach, we took quite a large set of small proteins. Particularly a few years ago when we did this work, ab initio is quite restricted in the size of the protein that can be addressed. So we limited ourselves up to 120 or so residues here. The two main messages that came out of this were that as the protein got larger, the chance of success diminished. And that's not surprising because it's harder, obviously, to make models of bigger proteins than it is of smaller proteins. Well, I say obviously, that's not really obvious, but it's true for ab initio models that larger structures are harder because of the sampling problem. The other message that came out of it was that we did very well with all alpha structures, but very poorly with all beta structures, and the mixed ones were in between here. But nevertheless, we could solve almost half of quite a large set of test cases. And although these were actually known structures, when we did the modelling, we treated them as novel folds, so there was no information from homologs in the PDB fed into the modelling. Just to give you an idea of what these look like, here's one of the targets we solved successfully. AMPL produced this cluster, and you can see straight away that some regions like the red and the orange here are quite similar between that set of models. Other ones, the blue at the back, are very variable. And like I say, it's a sign that the blue area is less reliable and the red area looks better. So the truncation in this case removed all of that blue area, left us this part here. We added side chains, and that could be automatically rebuilt using shellXC and ARP-WARP, I think, in this example. So you ended up with an essentially complete structure. You remember I say that we make search models ensembles across a range of sizes, and quite interestingly, we see success across that full range of sizes. So here is a complete model which came out reasonably well and was good enough to solve that structure. The search model ensemble is in pink. The target is in a spectrum. In this case, we had to truncate down the models about 50%, you can see, and that was enough to solve this structure. And then an extreme small case, because Phaser and shellXC are so good at placing and tracing these structures. This is, I think, is 5 residue fragment that was placed accurately and sufficient to solve that structure. If you want to try this, the very easiest way to do it is not to use Rosetta, which is what we were using for our ab initio modelling, but to use a server, a Quark server. And you can take the single output file that contains all of the models from that and paste it directly into CCP4 Online, click another button, and away you go. You get a lot more flexibility, however, if you do the modelling locally, because then you can feed in other information that you might know about your target, distance restraints, for example, as I'll show you. If you want to do it locally, then you need to install Rosetta. Quark is not available for local installation. And you also need to get some fragment files, that's the kind of raw material for building your ab initio models, from this Rebeta server. With that information, you can use either CCP4i or the command line, not I2 yet, unfortunately, but hopefully that will come soon. And the command line to use a file of Quark models would look like this. It's quite simple. For Rosetta, it's a little bit more complicated. You tell AMPL where Rosetta is installed, and you give it those 2 fragment files from the server. So that was fine. That was a few years ago. Since then, there's been a big explosion of excitement in bioinformatics, which is all to do with a way of predicting contacting residues based purely on sequences. And this has a lot of implications, a lot of applications, as Felix was talking about this morning. But we're particularly interested in it because it allows us to build better models ab initio and therefore solve harder structures by molecular replacement. So we've revisited the ab initio modelling quite recently, and we've tried to see if it helps us overcome these previous limitations. You remember we did very poorly with all beta proteins, and as we got towards the 120 residues, the success rate fell off. This is just a reminder of how contact predictions are best made. Ideally, you're in a position where you have a large number of sequence homologs, you make a big alignment. That allows you to spot pairs of residues in that alignment that kind of co-vary, correlate in some kind of way. And with the right statistical treatment, which has only been rediscovered quite recently, you can infer that those pairs are actually contacting in 3D space. And obviously that information feeds into this ab initio modelling in a very helpful way, allowing you to make better models. So this is Felix's work from last year. Just to orientate you, this is the target length along here. You can perhaps just pick out that dotted line there. That's our previous limit of 120 residues. We challenged ourselves with much bigger proteins, right up to 220 or so. This is the model quality up here. They're colour-coded by class, so as expected, we do better with all helical proteins, and in fact some quite large all helical proteins solve even without the benefit of contacts. These are the circles. But there are many other targets where the triangles and the squares, where we need that extra information from those predicted contacts to get models that are good enough to solve the structure by molecular replacement. And so with that extra information, we can solve quite large targets like this, and very beta-rich targets like these, which we would never have solved previously. If you want to try this, it's at one extra flag in the AMPL command line, or there's a task in CCP4 where you can paste in some contact predictions derived from a server and easily incorporate that in your local modelling. That's all globular proteins. That's where we started off. For various reasons, we got interested in other classes of targets. Turns out that AMPL is particularly good at solving coiled coil structures, which are considered to be somewhat awkward. Here are some successes in blue and failures in red. This is resolution here from high resolution to relatively poor, 3 angstroms at this side. And this is the length here. And you can see that we solved most of these. It's quite a large number in the test set, around 80% solved. And one important advantage here compared to other methods you'll see in the literature for coiled coils is that you don't need to try and predict whether your coiled coil is left-handed, right-handed, has 2, 3, 4 helices in it. You just tell AMPL the sequence and it will actually solve most of them for you. We actually, as a kind of baseline to see what the added value of the modelling was, we compared performance with a small library of ideal helices, and we could actually solve half of these with that library of ideal helices. But you can see obviously that 80% solve with the model, so the modelling is adding value. And an illustration of that is shown here. This is one particular example. Here's the crystal structure that we were trying to solve. It has a coiled coil with 2 helices and a small globular domain as well. The Rosetta model is not very good. This is a model of this, and you can see it's bent, shouldn't be. But the successful AMPL search model, although the modelling didn't work very well overall, once you've truncated it down, you're left with something that's valuable, because although the modelling didn't work very well, what we have here has captured the authentic kind of bend in this coiled coil helix. So different to that standard ideal helix, we've got the authentic bend that's emerged in those models, even though the global fold wasn't captured properly. And this is actually something we see regularly with AMPL, that the modelling may not work very well. Ab initio modelling is quite hard, but there'll be some local features, and we can often truncate down and capture some core region that contains those local features that are accurately predicted, and that's good enough with the benefit of modern software like Phaser to place it correctly and work our way up to a solution. This is work in progress where we're looking at transmembrane helical proteins. It also works reasonably well, perhaps slightly less well than we thought it might, but nevertheless we've got 15 targets here and we can solve 10, either with ideal helices or with standard Rosetta or with Rosetta including those benefit of the contact predictions, including some quite large structures. We're still working on this. We'll probably do better by the time we've finished with it. But you can try this already. There's a flag that tells AMPL that the target is a transmembrane. And of course, you can combine that with a contact file, maybe using ConKit to do the conversion and allow you to exploit that information as well. So I've mentioned the ideal helix that we introduced as a kind of baseline for comparison with the models in the coiled coil and the transmembrane work. That's a little library of 5, 10, up to 40 residue polyalanine helices. People have got in touch with us, actually, and we never really thought of using it for globular proteins, but a couple of users have got in touch, and they've had some success with using it in globular proteins. This is the one I know the structure of. This is a much larger structure that we only heard about relatively recently. This, of course, is quite similar to what Archambault does, and we're not doing anything anywhere near as clever as that. We're just trying to fit a bunch of helices, not trying to do any clever combination of hits. So it's not as clever, but it is quite quick, so it may be worth a quick try if your protein contains helices. And this is how you would do it. There's a flag for the command line, or again, it's very easily available through CCP4I. So that's all about making ab initio models. More recently, we've been thinking about how to exploit elements of the AMPL methodology to work with experimental structures as well. So both NMR ensembles and distant homologues, difficult cases. And a good way to kind of frame this part is to think about the truncation, which is a really key part of the AMPL pipeline, and think about other scenarios in which that truncation works for different reasons. So I explained that with ab initio models, the variable bits tend to be lower quality, so clearly they should be targeted first and removed. With NMR ensembles, the variable bits are obviously less well determined, perhaps less reliable, and certainly less helpful for molecular placement. So we can apply AMPL's truncation to eliminate variable regions in NMR ensembles. Where you have several distant homologues, we can also exploit the truncation to try and find the conserved core that's shared between those homologues. And that conserved core is actually more likely to be present in your unknown target. So these are cases at the bottom where you can find something homologous in the PDB, but it's actually too structurally divergent to work very easily with the standard tools. These are different approaches you can try at that point. And then finally, we've been sort of experimenting with ways to look at a situation where you have only a single distant homologue, and ways in which you can try and predict where that conserved core is, even in that single structure. And for that, we've been exploiting another recent bioinformatics finding, which has discovered that regions that are well packed and therefore quite rigid, they tend to evolve more slowly. And what that means is that we can use measures of rigidity or packing as kind of proxies for evolutionary conservation and truncate down on those bases, giving us something that would be evolutionary conserved and therefore more likely to be present in your homologue. So I hope to show you these just quickly. I won't spend much time on this, it's already published, but AMPL works very well with NMR structures. This is a comparison with FindCore, which is a specialized tool for dealing with NMR for molecular placement. And the green and the blue show cases where the RMSD is higher and the sequence identity is lower, and where AMPL worked and FindCore didn't work. And you can try this, the command line or CCP4I, you just give it a flag and a PDB file of your NMR ensemble. So moving on to the crystal structures and ways of dealing with distant homologues. What you're often faced with is a situation like this. Your target may be one of these, and you can see by the sensitive methods we have these days that the other there is a structure in the PDB. So imagine this is your target. You can see in the PDB this is homologous, very distantly homologous. Clearly, no amount of editing of this by hand is going to solve this for you. So the challenge is really to think of a way of extracting the small region, the small conserved core that is in fact shared between the two. And you can see it agrees very well. It's hidden in these very different structures. How do we identify this conserved core in one of these and try to solve the other one with that small region? And with multiple structures it's easy because we can superimpose those structures and see which parts are conserved. Like I say, with single structures it's harder, and we're using a proxy. We're trying to find regions which are rigid, and we think those are more likely to be evolutionarily conserved. So this isn't published yet, and we haven't tried it on a large range of proteins yet, I must admit, but the results so far seem quite promising. What we did here was look in a superfamily. We extracted 7 distant relatives, or shared only low sequence identity with each other, and we said if we take these 3, can we solve the other 4? We'll take superpositions of 2 or 3 and see if we can solve the other 4. And if I make this animation work, you'll see that Ample trims down from this common region, leaving us with the region at the end of this sheet, which is indeed where the catalytic site is, and therefore the most conserved part in that structure. So it seems to be working quite well. And sure enough, when we compare Ample here against standard Mr. Bump, we can see straight away there are targets that Ample solves, where Mr. Bump doesn't. Don't worry about these numbers. And Mr. Bump is also quite sensitive to the presence of one of these 3. If you don't have that, the other pair doesn't work, whereas Ample generally works with any 2, and especially 3 of those. So you do get more value in these difficult distant homology cases by this kind of superposition and truncation approach. You want to try that at the command line. You need to tell Ample that the sequences of these structures are not the same. It will then do a different kind of superposition, but you basically just give it a directory with some structures in, and it will do the rest. So finally, the idea of what you do if you have a single distant homologue and it's not working straightforwardly. The idea here is, like I say, to try and try and truncate down to a conserved core, which in this case is just there. You can perhaps see those stick residues. That's the catalytic site. So like I say, we know that flexible regions are more evolutionarily divergent. We can see the flexibility using this program Concord. Concord, just to give you an idea, will look at information in this starting structure, for example, distances between residues, and will then use distance geometry methods to produce an ensemble of structures that satisfy that information. And so what you see is regions like the red region here. They're not very well packed, they're not constrained at all, they come out as very variable. And those would be the regions that we would think are more evolutionarily divergent, and so we'll get rid of those first. And this region here, where the catalytic site is more rigid, more packed, and so that will remain. You see the truncation happening here. That catalytic site at the end of this sheet remains right until the end, and so we truncate down to some small core. So that's the automated side. For a comparison, we asked Olga to produce 4 expertly edited versions, what she would try if she had this. And then we ran the comparison again, and we got some very good results here. So Concord, through Ample, solved 5 of those 6. Regular Mr. Bump could only solve 1. And the point I want to emphasize again is that sometimes we had to truncate down quite dramatically. These are successful search models. I think the battery's going here. The top right, those are successful search models. They're obviously very small, highly truncated, and sometimes that degree of truncation that you'd never think about doing manually yourself is actually required to get successful structure solution here. So if you wanted to try that yourself, this is how you run Concord. It's 2 very simple commands, takes up to half an hour at most, and then you simply have a directory with those structures in, tell Ample where it is, and away you go. So I'm going to finish there with some thought, a summary on when you might think of using ample, when it might work for you. If you have a novel fold or a very divergent globular fold, then you should think of ample, provided it's not too large. What does too large mean? Well, if you don't have information from contacts, I would say 150, 200 at a stretch. If you do have information from contacts, then you could try up to 250 residues. So, relatively chunky-sized proteins these days. If your target's a coiled coil or transmembrane helical protein, then definitely give it a go. If you have one or more distant homologs that don't work easily, then there are approaches in ample. And likewise, if you're working with an NMR structure ensemble, it's definitely worth trying. I've shown you, as we're going along, the command line, CCP4I. At the moment, CCP4 Online, the server that Ronan mentioned, only runs a relatively restricted set of ample functionality, so you basically provide it with a file containing models that allows you to work with those quark ab initio predictions or your own set of models. We're hoping to improve the functionality on the server quite soon. People look at these complex pipelines and think, oh, it must take a very long time. No, it's not really too bad. Everyone's got multi-core workstations on their desk these days. So these are some timings that if you're going to do your ab initio modeling locally, using the fragments, you can put aside a day or so for a complete job, including the modeling. So it's perfectly manageable these days. Acknowledgements. I want to thank these excellent guys in Liverpool who've done most of the work. Ronan's also been heavily involved. Martin Wynne and Olga, who's now at Constans, give really valuable sort of strategic oversight of the whole project. Thank the funders, and finish with our website where you can go for more information and some tutorials. And thanks.
Thanks very much, Dan. We've got time for a quick question. I know we're keeping you from tea. So I've got one question. Do you use the SCOP or CAF nomenclature to help you identify cores at all or anything like that?
No, that would help divide into domains. We actually, a core, I would say, is going further. It's saying, your domain is 100 residues, but the bit that's actually really well conserved across a superfamily is, a core of 30 or so. So I would, SCOP and CAF are useful for defining domains, but we're often going a lot further in our.
So what about ProSite in terms of looking at site residues?
That's not really.
Okay. If there's no further questions, we're running a little bit late, so I'd just like to thank all this session's speakers and remind you to be back here at 4:30 for the start of the next session, 4:30.